Hi class, this is Miss Mackenzie. I'm going to make you a video with kind of the rest of our review for the business calc. So let's start with solving some equations that have exponents as our x is in the exponent, so they're exponential. And you're not seeing things. I have one lens in my glasses. So hopefully tomorrow my surgery goes well. Okay, and I can see again. Let me go ahead and share my screen with you. And you should be able to see me in the corner, and then you'll see my paper here as well. So what we're going to look at here is, or the first problem I want to look at is something like this. What if I have 5 raised to the 8 minus 7x? And that's going to equal 5 raised to the 4x minus 2. So I have both the bases and an exponent. What we should notice right away is we have the same base. So they're both 5 to this power. So it would make sense if these two exponents equal each other, then that would be our solution that would work for both sides. So what we're going to do from here is we're going to take and make our exponents set equal to each other, and then just solve that equation from there. So if we want to keep it positive, we can add the 7x this way, right? So these ones will cancel. 4 and 7 make 11x. I still have the minus 2. I still have the positive 8. Then I add our 2 over, and I'm going to get 10 over here equals 11x. I'm going to divide by that 11. And I'm going to get a fraction. That's all right. My answer is 10 11ths. Okay, so 10 11ths is going to be our answer for that one. That means if I put 10 11ths in up here and I multiply and add, I get the same number. So it's going to bring 5 to the same power on both sides. So if I have an exponent, I can solve it that way. What if I have something like 2 to the 2x minus 1 equals 4 to the 5x. Okay? This time, our bases aren't the same. So what are we going to do? Well, we have to look at the base and see if possibly we could write one of the bases with the same base. So I didn't say that very well, but basically we can write 4 as 2 squared, so then it would have the same base as the left side. So what we're going to do from here is we're going to keep this side 2 to the 2x minus 1, and over here on this side, we're going to write this as 2 squared. So when we do that, we're going to add that 2 up by the 5x, and we multiply those together to get what's going to be in our exponent. Now we're to what we just saw, so we can set the exponents equal to each other and solve, and this one will be 10x over here. I can minus over the 2x, and I'm going to get 8x, divide by the 8, and I get negative 1/8. So if I put in negative 1/8, it should solve both sides. Okay, so this is, we have an x in our exponent. This is one of our methods. All right, so this kind of brings us into the idea of a log. Okay, so let's start with reminding you just how to change from exponent form to log form. So if we have something like log base 2 of 4 equals 2, how would I change that to make it look like exponent form? So right now that's a log form, and in exponent form, it's going to look like, the bases stay the same. So base of 2, and then it's going to go to the power of the answer equals the 4. So when we solve the log, look, when we solve the log, we are getting the exponent. Okay, so we're telling what is the exponent. So we should be able to switch back and forth between these two forms. Okay, Also, just a reminder, when you see log on your calculator, just a log, it is base 10. So we're kind of lazy there. So we need to remember that. And also, if we do a log base E, that's the same as our natural log. So if we're solving something that has compound interest, the formula has E in it, and we're going to have to use the natural log to solve it because the natural log has that base E instead of a traditional log. Okay, so just a reminder on that. Another one to remind you of maybe is the natural log of E is asking, remember this is the same as natural log of E, so it's saying E to what power equals E. That's what that is asking. So E to the 1 power equals E. So natural log of E is 1. We'll use that quite a bit as well. Okay, I'm going to switch papers real fast. So let's look at, well, this first one doesn't really take logs to solve, but we're gonna get to the log part. So we're gonna look at some examples of using some of those financial formulas. So hopefully you've seen them before. If not, you'll get better at them, but they will come up quite a bit in business calc. Okay, so what does this ask? This says, I want 20,000 cash for a new car in 5 years from now. So now how much should be placed in an account now if the account pays 5% APR compounded weekly. So this is a compound weekly. So remember, weekly tells me that in value, and that's going to give us, weekly is going to be 52 weeks. So let's remember what the formula looks like real quick. Okay, the formula is, well, A usually stands for our future value. So what's it going to be worth later? So our answer, our future value equals our principal, our starting amount. So for this, you want 20,000 cash. Okay. And then that's not our starting amount. We don't know how much should be placed in the account. So we don't know P right off the bat. And then 1 plus the rate is 5% divided by 52 for our week times our years. And that was given 5 years. So let's plug in that information into our formula. This one gave us our future value. What's it worth later? So that's our A, and we're going to put in our 20,000. And we don't know our principal, what we're going to have now. Then we have our 1 plus our 5%, our 0.05, divided by that week's 52 weeks. Then we see we also use the N up here as well. And that's 52 weeks times our 5 years. So let's go ahead and solve this. So the first thing we're going to do when we're solving for P is we're going to calculate this number over here so we can divide it into the 20,000. Okay, so I went ahead and I put that in my calculator. There's not really a shortcut way. Just make sure you use the parentheses up in the exponent as well as here, and make sure you get the same answer as I did. And you could pause the video and try that if you want. So when I divide that 20,000 by the 1.28387, we're going to get $15,577.89. Okay, so I have to put 15,000 in my account now to have 20,000 in 5 years. So, and that's pretty realistic. 5% is actually kind of high for an investment. Okay, so we could see something that is compounded continuously, and it can be, this starts to bring in that E, so it's slightly different. This could be money. It could also be bacteria in science. It could also be population. So let's take a minute to look at an example with population. So our population is 42 million. Our growth rate is 1.09%. I don't know if this is true. I got this from the book. what is the population in 9 years if it's compounded continuous? So this formula up here is compounded, but not continuous. It's either monthly, most common, weekly, yearly, quarterly, which is just 4 times a year, bi-weekly, you could do semi-annually. So this compound is not continuous. So our formula for continuous looks like this. Now I put an f of x in there because this is population. It really could be a, which is again our future value. Okay, so for this one, we have our principal, that's just our starting amount, and we're going to times it by e to the rate times time. So notice we then bring in that e. So for some of these, we're going to have to bring in the natural log to solve. Not quite yet though. So let's go ahead and put in the information we were given. We were given not the future value. We're actually looking for that future value. We were given 42 million, which we're not going to write all the zeros. We're going to do it in millions. And then we were given the rate. We had to move the decimal 2 places, 0.0109, and then we're going to times it by the 9 years. So what are we going to get? We're going to get 46.3 million. Again, I said A there, f of x or a, interchangeable. A lot of times when it's population, we like to use f of x. Okay, so that's an example of compound interest and compound continuous, straightforward. Now let's take a minute to look at one where you have to solve using a log. So for this one, I am going to write the compound. I won't start from the word problem. I'm just going to start from the equation. So this is my third example in this, I think, or maybe whatever. It's okay. It might be my fifth. Meh. Okay, so what if I had something like 10,000 equals $500, and it's 1 plus 0.06 divided by 12 to the power of 12 times t. So what is this formula saying? It's saying I want 10,000 future value. Right now I have $500. My rate is 6%. I'm compounding it every single month, and I don't know time. I don't know how long. So what's the difference here? Last time I had an A and a P that I solved for. The difference is it's in the exponent, and I can't solve those without a log, okay? So we're going to simplify this a little and then use our log. This 500 is being times, so I'm going to start by dividing the 500 over. So 10,000 divided by 500 is going to give me 20. We are trying to get 20 times the money we started with. Holy moly, that should take us forever, right? I mean, it would be nice if we could put money in an account and get 20 times our money in 5 years, but this is not looking very doable. It's going to be a long time. So from here, what else can we simplify? Well, we could simplify in our parentheses. So I'm going to use my calculator, and I'm just going to say, all right, what is 1 plus 0.06 divided by 12? That gives me 1.005. So that's as simplified as we can get. Okay, so now I'm here. So what I can do from here is I can magically add in a log. I don't have to use a natural log. I can, doesn't matter. If some of the calculators, the natural log is actually easier to find than the regular log. So, or log base 10, they're both a regular log. It doesn't matter which one we use. So we can use our regular log base 10. We don't have to write the 10. And all we're going to do is first write that log in front of both sides of our parenthesis. And what that log allows us to do is bring our exponent down. Okay, so now I'm going to be able to bring this exponent in front. So I'm going to keep this log base 20 over here, or log 20, not base 20. And then now I'm going to have 12t times log of 1.005. So now these are all just numbers. So I can solve for t. So I'm going to need my calculator. Of course, I have the one that actually you can't find the log very easily on. Let me grab my other one real fast because I don't really know the solution. So I'm going to take log base 20. Clear on. Okay, so on this calculator, logs over here, natural logs right below. So I'm going to do log of 20 into my parenthesis, and that gives me this number here, 1.300 whatever. Okay, and you're going to want to go out quite a ways because my math lab will be picky. It will say if it wants out to 3 decimals, you better go 5 or 6 so that you can round correctly. So let's just go on the safe side and go about 5. So 1.30103. Okay, over here I still have this 12t, and now I have to calculate this log. So log of 1, dang it, I can't see that very good, 1.005, and I get 0.002166. You can see that there. That's this number. I'm going to actually times it by 12 also. So I'm going to leave it in the calculator handy. 21661. I went out a couple extra places on that one. I'm going to use the calculator and times it by 12 so that I get what those two numbers are together. And now I'm going to have 0.0259927t. And this one's 1.30103. Okay, now I can divide. You can actually scroll. Oh, I thought you could. Second entry. Nope. This calculator won't. It's not smart enough. Some of them you could scroll up, grab that number, and divide. Then it's in exact form, but it's okay. So we're going to type in 1.30103, and I'm going to divide it by my last answer, and I get 50.05. So 50.05. So it's going to take me about 50 years, right? 51 if you want to make sure you get enough money, right? Or get exactly there. So if that would have been like 50.3 even, I would have been rounding it to 51. Just because even though it's not to that 5, it's going to take you that additional year to get to your goal. Okay, so we're at 50. So we used a log. Okay, so same kind of idea. Let's do one that requires you to use a natural log. What if I have something like I'm tripling my money and it equals e to the power of 0.05 times t, something like that. So this is realistic. You're tripling your money. I didn't start with any money. We're just asking, how long will it take to triple your money? Okay. So maybe we start with $1, we end up with 3. That's kind of what it looks like right now, which is totally the way you could set it up if it says double or triple. It's like, okay, I invested $1, which I imaginary right there, and I got to 3. So this time it has the E, so we can't simplify like we could here because we don't have a parenthesis. We're going to just write in our natural log on both sides. Now that's going to allow me again to bring down my exponent. So on the right side, I'm going to have 0.05t times natural log of e. Now what is the natural log of e? It's 1. So that's going to drop off to 1. 1 times anything is itself. So now I'm here. So I can take the natural log of 3 in my calculator and divide it by 0.05, and I will have my answer. So natural log's over here. So natural log of, what did I say, 3, into that parenthesis so you don't have the other part in it, and I'm going to divide it by 0.05, and I get 21.97. 21.97 equals time. So really, it'll take 22 years to triple your money at the rate of 5%. Okay? All right. So that's kind of an idea of how to use those logs. Now, there are a lot of other log rules, but honestly, this is the most important for us, and we'll use this right here more than one time. I'll always show it to you, but this will come up over and over again through our class. One more problem. I want to show you one that has range and domain that kind of has a log in it. So what if I have y equals -1 plus the natural log of x minus 11? We have the natural log of x minus 11. So we are saying here that we have a base of e. What is this saying here? It is saying e to what power gives you x minus 11? That's what this is asking. That's what that natural log is asking. I'm getting out an exponent, or I'm getting out, I'm getting out e to what power. So no matter what I put in an exponent, whether it's negative or positive, I get a number answer that's not negative. So remember, if I put in a negative exponent, I get 1 over that. So for example, just on the side over here, if I had x to the -3 power, I would move that to the from the numerator to the denominator and keep that same power. So when I have a negative exponent, I'm really going to get out a smaller number, but it's not going to be negative. So this will always be positive. So when I'm asked, what will be your domain? Okay. How could this end up being restricted? Okay. So how could this end up being restricted? Well, we're going to end up having to have this part here is going to have to be positive, because e to what power will equal this? This has to be positive. A little tricky to think that through, but x minus 11 has to be greater than, and it can't equal 0. Okay, you can't get 0 because anything to the 0 power is 1. So basically, this is what you're getting out as your answer. E to what power is that? So anyway, I keep saying anyway, whatever. Now you're going to count them all and see how many I said in my video. So then from here, I can see that x is going to have to be greater than 11. So our domain is restricted in this log problem. We don't do a lot of logs. They do have a restricted domain if you start with a log in a problem, but we just don't do it as much. I don't even think we wrote it down. We just wrote down that x in the denominator and a square root, but it could happen if it's written this way specifically. And our range, what we get out, well, I don't know if for this one, I think our range could be any number, because this would be greater than 11. Yeah, I think we're at all reals, but we're good with just the domain on this. Range would be all real numbers. We did the range on this one, because we could get out any number, especially with adding it to a -1. Well, not that that would play too much of a deal in there, but had me thinking. I would have to look at the graph and double check. That's just how the range works for me. Okay, so you have the rest of that review. I did not cover everything. I'm just trying to highlight those ideas from 1400 that you should know in order to really get started in this course. And I will see you all on Monday.